Hello. Today I'm going to tell you all about a prominent technology that underlies my master's research here at the U in the Composites Laboratory. That tech is carbon nanotubes, and specifically their application to ultra-high strength materials. So, what is a carbon nanotube? By definition, it is a large molecule made up of purely carbon atoms that is slender and shaped like a tube. These tubes are very small in diameter, just a few nanometers, but can be up to several millimeters in length. Now, this structure may look familiar to you as being similar to another material, such as diamond or graphite. Diamond, graphite, and carbon nanotubes are all allotropes of carbon. Carbon-carbon bonding is incredibly strong, and the 3D structure of diamond takes advantage of this to provide hardness and strength in all directions. Graphite forms in individual planes, a 2D structure, and as a result it is incredibly weak and shear and does not take full advantage of the high carbon-carbon bond strength. CNTs take advantage of the strong carbon-carbon bond in a high aspect ratio 3D structure that is extremely strong, stronger even than diamond. To outline this tech update, we will first talk more about the high potential for these CNTs. Next, we will talk about how CNTs are made, and then scale up for use in mechanical structures. And lastly, I'll explain some other notable properties, namely electrical and thermal. Let's jump into the potential for CNTs, best visualized with an Ashby plot, something most engineers are probably already familiar with. An Ashby plot is a way of visualizing how strong and light a material is. Strength is on the vertical axis and density is on the horizontal. Now metals are in the upper right because they are both strong and heavy relative to other metals. Foams are on the lower left because they are very light but also very weak. Diamond is located at the top, but it is lighter than most metals. Now composites have been created in an attempt to reach as far out towards the upper left of this plot with stronger and lighter materials. Carbon fiber reinforced polymers are the current standard for composite aerospace structures. But CNT reinforced polymers have the potential to be even stiffer and lighter, an obvious advantage for applications where weight is critical, such as for commercial airlines and space exploration. Moving on to the synthesis of CNTs, which can happen in a number of ways, of which I have highlighted the three most popular. Chemical vapor deposition, laser ablation, and arc discharge. Now, I'm not an expert on any of these techniques, but to give a brief description, in CVD you are basically growing CNTs layer by layer on a substrate. Now this is how aligned CNT forests are created. Laser ablation involves focusing a high-powered laser onto a target rod made of carbon. This high energy causes CNTs to form, which are then trapped and collected. Arc discharge uses graphitic electrodes to create an arc of electricity. This high-energy process also results in the creation and collection of CNTs. Both laser ablation and arc discharge will create randomly oriented CNTs, and the strength of a CNT is higher axially, and so it is desirable for these CNTs to have some degree of alignment. This is an SEM image of a CNT forest that highlights the true geometry of these nanotubes, and that it is less than perfect and often has some curvature. This is a depiction of randomly oriented and entangled CNTs, created from something like laser ablation or arc discharge. These CNTs can become more aligned if stretched. So far, we have shown that CNTs are incredibly strong and can be made in large volumes, randomly oriented, or with some degree of alignment. Now, how do we create high-performance structures with CNTs? This is a current research area being heavily invested in by NASA, and currently they are using yarns and hybrid composites to realize these structures. CNT yarns came about as a way of achieving a quasi-continuous reinforcement with a high degree of axial alignment. They also have the added benefit of being comparable in diameter to traditional carbon fibers, making them easy to process into CNT yarn reinforced polymers. This process is very complex, but at its core relies on van der Waals forces between each CNT to hold the structure together. Another way to make use of CNTs in large structures is by combining it with a traditional carbon fiber composite, or a hybrid. The most common use of CNTs in hybrid composites is to provide an increase in interlaminar strength, which is an inherent weakness of traditional layer-based composites. They do this by placing vertically aligned CNTs between existing layers in an existing composite. CNTs have also been used to create honeycomb structures that are lighter and stronger than their paper counterpart. Lastly, CNTs can be mixed with polymers or metals and 3D printed, creating structures with enhanced mechanical, electrical, and thermal properties. In addition to having superior mechanical properties, CNTs also have very unique and useful electrical and thermal properties. These include high electrical conductivity and a high in-plane thermal conductivity combined with a low through-plane thermal conductivity. The electrical conductivity has applications in thin sheet heaters and power transmission. Thermal properties allow for uses such as aerospace heat shielding, in which all of the heat will be transmitted outwards and around the spacecraft rather than into it. That concludes my brief introduction to carbon nanotubes and their application to ultra-high strength materials. Are there any questions?